Okay, so I'd like to welcome everybody, including the people in the room and online, to the final session, the final speaker of today's workshop. So I'm very pleased to introduce Sebastian, who is from the ETH Zurich and is actually originally from Switzerland. You're entirely Swiss, except for the 8 years that you spent in Israel at the Weizmann, where he learned Hebrew at lunch. I'm very impressed. And he's going to tell us something today about his work on topology to applicate from topology to applications with mechanical metamaterials. Thank you very much.
Thank you very much. But I think if I stand next to that, that should be fine. But let's see. I catered to you guys here, and those in Zoom hopefully also hear something. Thank you very much for the introduction. Thank you for the invitation. I had already a great morning, a wonderful lunch, and I tried to treat you with a bit of what we did in the past. I start out with thanking the people that what I'm going to tell you about today was mainly pushed forward by Mark Serra-Garcia and Dana Dubček. And you'll see what this is all going to be about. Someone is paying for our research. That's also very nice. Let's get started. We do topology in classical systems. I want to take a few minutes to kind of get there, to build the bridge, and I start with this slide. So this slide these are two mysteries. There is a double slit experiment and there is a quantum Hall effect, and both of them are very strange. One is a matter that actually interferes with itself, and one is a plateau that shouldn't be as flat as it is. And of course, both of these mysteries have long been resolved. One is we introduced quantum mechanics, and we know that particles are also waves. And that's the Schrödinger equation, and that solves that mystery of why there is a double slit phenomenon. Using this equation, you can actually also resolve this mystery, because you just do two-dimensional electron gas in a magnetic field, and you calculate and you find this is what you should happen. It's the quantum Hall effect. So these two mysteries have been resolved with the Schrödinger equation for 2D electrons in a magnetic field. The question is, and then, once you have that, you actually put it to work, right? You say, I have a 2D electron gas, I put it in the magnetic field. I'm not yet mastering that pointer very well. I get Landau levels, and then I get, bulk states that are these Landau levels. I'm really not mastering it. And then I get physics on the surface, which are these chiral channels that we saw in the morning, very nicely introduced by my friend. This is a result of putting the Schrödinger equation to work. And now the question is, how can I take this over to classical materials? And the way there is, as it typically goes, these magnetic fields are annoying. It's a gauge field, and I don't want to be bothered with it. Let me write down a simple model. And what you see here is just a simple two-dimensional model on a square lattice with some phases that you acquire when you hop. It's a model for a magnetic field on a lattice, I know. But then you write down the Schrödinger equation again, which is just a tight binding model. And now we get closer to where my world actually is. We have a psi I at some site that changes as a function of time given by the Hamiltonian, which is just the matrix in that space of lattice sites on my square lattice. Having that simple model, like carries the same physics as the quantum Hall effect as I showed before, now I can go to classical mechanics. Because if all of these physics of having bulk states and surface states that have spin momentum locking or whatever degree of freedom, momentum locking, if it is there, then it must be somewhere in this HIJ. It has to be somewhere in this Hamiltonian. Now, if I just replace the psi with some displacement field U and my H with a dynamical matrix DHJ, which is just, masses and springs connected. So this DIJ just tells me how is one UI connected to another UJ with a spring in between. Then, if I take the same structure for DIJ as you have in your Hamiltonian HIJ, the eigenstates are going to be the same. So the whole physics of having something in the bulk, something on the surface should survive. And that's really where we make that bridge from the quantum mechanical world to the classical world. And of course, you tell me, no, but I need spin, and I need this, and I need the orbitals, and what have you. But I can always, my displacement field doesn't need to be a 2D membrane with a scalar displacement field, right? I mean, in classical mechanics, I can have arbitrarily complex objects that might have a direction in which I pull my ball out of its equilibrium position. So I have an arbitrary alpha beta structure of internal degrees of freedom of my displacement. So that is just to showcase that most probably I can get arbitrarily complex setups to play with this thing. And that's the question I'm after today, is one of the fascinating physics that I think I showed us this morning with topological bands can be reused or used for technologies in the classical ways. So that's the question I try to answer. That's the goal for today. And I already give it away. Yes, there is something, but really not what we wanted there to be. So bear with me. I tell you a story of how we set out and what we tried to achieve, and then what eventually we did, which is maybe closest to something I would dare to call a route towards a technology. So that's just now you know everything. You can fall asleep. I will talk only about mechanical degrees of freedom because that's what I do. But of course, topology in classical waves doesn't need to be a mechanical degree of freedom. It can be any classical wave equation. In particular, Maxwell's equation is something people push very far, and there are beautiful, not only experiments, but also routes towards technologies. So what Mohammed Hafezi showed us, that you can do frequency comps that overcome some limitations typical frequency comp setups do not have. Then from Motisegev's group, we have a topological laser. So they put with photonics, with light, they put this topology at work. There are applications. Now, I think they would both agree with me that these are beautiful examples of technologies, but whether they outperform the conventional way of achieving the same thing is yet to be seen. So also there, you know, we have a wonderful route towards technology. We're not, there is no market-ready product there, I think. What are we doing? We design phonon dispersion. That's, in one sentence, what we like to do. So what you see here is a block of iron, actually. And then there is, of course, a phonon band that has a momentum, it has a frequency. And what we do, we shape this phonon space. That's all we do. And actually, we only do it in one way, because we're simple-minded, we drill holes. Or, to be a bit more precise, but geometry is our design toolbox. And of course, the moment you drill holes, you know, if you drill holes every 5 nanometers or you drill a hole every 2 centimeters, you're gonna choose which frequency range you address. So in that sense, we're somewhat scale invariant up to fabricational limitations. And that's very different to the 2 talks we had in the morning, where you guys, you put elements together, you try to find out what are stable crystalline structures that then have some electronic properties. So where your design, or one of your design toolboxes is just chemical composition, for me it's geometry. So it's on a different scale, and that's why I call it metamaterials. There is a very strong metamaterials community that would only say it doesn't count as a metamaterial, it doesn't use local resonances and what have you. I'm much more liberal about the use of the term metamaterial. I try to implant behavior, phononic behavior in materials that the bulk material wouldn't have. So that's what we do. And now there are flavors of topological mechanics, and the flavors really are defined by what is the medium we use to do this. And one thing we already said is that discrete kind of ball and spring models. And that's a very trivial thing because, you know, I can write down that Hamiltonian that I have from whatever Haldane model or a double Haldane model or what have you. I can just build with balls and springs. And that's nice. it's nice to show that Newtonian mechanics allows you to observe certain topological effects, but it's not particularly challenging. I mean, this is, we did that with pendulums, and we did that a long time ago, and this is 0.5 meter long pendulums, 0.5 kilo heavy, and they show a quantum spin on it. It's nice, but it's an illustration, it's not a material, it's not an application, it's just a playground. But it's a versatile playground. Then the second one are acoustic waves. It's again super simple, it's a scalar wave. So everyone can solve the scalar wave equation, and it's again extremely simple to implement model ideas. And also here, that is something we did in various forms. We built, you know, Weyl system that showed axial magnetic fields, where the magnetic field has a different sign on the two Weyl points. We built a fragile topological band structure and showed its spectral signatures. So, you know, this is nice. It's a toolbox, but it's toys. It's you know, it's important toys for me. And why is it important for me? Because dealing with this fragile topology, you see the sample there in the back, allowed me to gain much deeper understanding of fragile topological bands, which then allowed us to make progress also in the description of superconductors. Now, our collaborators in Princeton, Andre, when he wouldn't meet that experiment, because also Maya, she understands fragile topology from the outset. I didn't, but the experiment helped me. So that's just our playground there. I also don't want to talk about that. I want to talk about the really nasty beast in the middle. Elastic waves are, you know, it's a tensorial wave equation. It has longitudinal and transverse polarizations, unlike the Maxwell equations. It's horrible. And that means bringing your ideas to work in this round is much more complicated, much more challenging. But it turns out you're much closer to an application, because shaping something out of a silicon wafer is something that you can scale down and then have in your cell phone, whereas you don't have an acoustic metamaterial in your cell phone, neither do you have my 0.5 meter long pendulum. So that's just me advocating elastic waves, but in order to do something there, we need to develop some technology, and I want to show you one example, what kind of technology we developed to design these band structures, and then show how we put it to eventually work for an experiment. And that's the first part is really, we wanted to see a higher order topological insulator. It's on the market, you read one morning the archive and you see something about a quadrupole insulator and you feel like, wow, that's a cool thing, I want to see. And then you say, okay, but how do I do that? So let me make it out of some silicon wafer. So that was the thing we wanted to see. But then we realized this is a hard thing to do, and we needed to develop some tools, and that's what I'm going to do. But before I show you which tools, I just want to show you a bit of why we have been fascinated about this higher order TI, because at the end of the day, this fascination of you know, some garden variety theoretical physicists like me getting excited about a topological band effect, then driving us to develop a toolbox that helps us in other ways, I find somehow, I shouldn't praise myself, and I don't praise myself, but what I want to say is we followed our kind of excitement for something and created something that is useful at the end. So let me show the excitement. But all the topological insulators up to these higher order ones could in one way or the other be cast into this dipole-based scheme where you say I may or may not have a dipole moment in the bulk, and if I have, then if I put it in a box, well, I never have any charge accumulation in the bulk because there's always a negative and a positive one, but then at the edge I will have uncompensated charges, and that's a picture I can have for all the, you know, quantum Hall effect and spin quantum Hall effect and the 1D system. So that was the conventional lore, and then what came about is that if you have a quadrupole moment in your bulk, then also in the bulk you don't have any charge accumulation because you always have the compensating charges. You don't have any surface charges either that build up because they are also compensated, but then you have something on the corners. And that was put forward by in this, my opinion, very important paper, and very important, just very beautiful paper. And we said, wow, we want to build that. That's what we want to have, but can we understand that? And indeed, they also showed us how to characterize it, how do you get a grasp on this quadrupole moment in terms of the topology tools we know, and it's Wilson loops as we know them from conventional TIs, but now you have to do nested Wilson loops. Also not so surprising because you need to go 2 dimensions lower. But all I want to say is there is a theoretical framework to say whether you have such a thing or not, and that's, if you even have symmetries, then something is quantized, which are these nested polarizations. So that's was set on the table. This is a new theoretical tool. Can we build it? Nice enough they were. And they gave us they gave us a model. And the moment you have a model and you are in this game of knowing how to shape mechanical metamaterials, then you're almost done. But the problem here is almost. In that case, the model that you see here is a hopping model on a square like this. Many of you will know it. It's just a dimerized hopping model, meaning you have weak bond, strong bond, weak bond, strong bond, like in an SSH chain, but you have it in 2 directions, but you have an additional pi flux. So whenever there is a red bond, I pick up a minus sign if I hop over it. So you see that every plaquette has a minus, has 1 link minus. So if I now have to build this in a mechanical metamaterials, or in a silicon wafer really, that I carve holes into, I have to have local resonators that correspond to my state at this site. But then I need to have well-controlled hopping strengths, and one of them has to be of negative sign. And if you go to the shop and you know, you look for springs, they all have a positive spring constant. And that means that you need to work a bit harder to get that. And then it shouldn't only be negative, but it should have exactly the same strengths as that black one, but of the opposite side. So you need to have a way to implement this, you know, we would call it reduced order model or tight binding model or effective model. We need to embed this in a high dimensional manifold of elastic waves. So that was the challenge that we needed to solve. So this is what we wanted to build. This is a silicon wafer with little plates that have some vibration frequency, and then you see these arms that connect them that should give rise eventually to that effective model that I've shown you before. But if I give you this and ask you what is the effective model describing this structure, that task is almost trivial. Because you look at what is the mode here, what are the mode of these plates, and then you see these arms, and then, most probably if that mode spins, then it will excite this one. So distilling an effective model from a high-dimensional manifold, going the other way around is what we call an inverse problem. It's very hard. And that is a challenge we need to address. And the path we took is what we call perturbative metamaterials, and I explain you what it is. We take single units, these are plates, and then they have vibrational modes. First, they have a number of rigid body modes where they just wiggle like this, zero frequency in the beginning. Then we have the first modes that actually bend. So we have this dxy symmetry and the dx squared minus y squared symmetry. So these are my local resonators. This is like my orbital at this lattice site. And now I couple them weakly via a small link that I put in between these modes. And now if I couple them weakly, I'm not going to shift their frequency up to this mode or down to the others. So that's the perturbative aspect there. And now I can ask myself, okay, if I build such a link here, such a bridge, what is going to be the combined mode? And then I know I have a bonding and anti-bonding mode, and from the strengths of how much they shift, I know the strengths of this coupling. And I can actually do 2 signs of the hopping strength. You see, if I put the bridge on the same side of the node, if this is pulled up here, then also this thing is pulled up. Whereas if the bridge is going over 2 sides of the node, I actually excites the other mode out of phase by pi with respect to this bridge. And this gives rise to two different signs of the coupling strengths of my system. So now, starting from here, I know what is one mode doing. I can make a database of coupling strengths given this small bridge, and then I know the two-plate system, and then I can go on to the full lattice system. And the whole thing works because it's perturbative in these couplings. And then you run through that thing, and then you also realize, oh, but because not all plates or not all modes have the same strengths of couplings or around it, or some have two negative and some have only positive. So then the arms will attach at different places. So you actually shift also a bit their frequencies. So you start drilling holes to adjust for that. And then you have a working loop where you have a way to connect the geometry to the effective mode. And I say going from here to here is trivial, and that's what you see here. Here we just evaluate what is the effective model for this structure here, and it's given. So that's a technology we invented, if you want, for that higher order TI, and that's in this nation materials here. We describe in great detail how you do that. And then we were able to actually implement the one model that we wanted. You can analyze then this model in terms of the nested polarizations, and you see that from a theoretical point of view, you succeeded, but then you want to go and check that it works. So what you see here is one of these plates. They're very big, so we're not yet on the cell phone size, but you know, going from here down is just, you know, getting better lithography in place. And we have a 10 by 10 system of this sample. And then what we do here, I think I have a better picture here. Yeah, exactly. We excite a plate here. We excite with a laser. We excite with a ultrasound transducer. We excite a plate, and then we have a laser interferometer, and we measure how much this plate is modulated. And then we scan the frequency of our exciter, and we just take a screen. So that's a typical result we get, and we can start analyzing it. So below 60 kilohertz, we have all these solid body motions of the single plates that now develop into phonon bands the moment you couple them. And this we don't want, and we arrange the whole setup such that these rigid body phonons, these rogue phonons as we call them, they end at the frequency of 60 kilohertz. And then you have two more of these modes here that are the DXY modes, and then anything above 85, 90 kilohertz is again modes that we don't care. So these are the dx squared minus y squared modes, and these are the modes we really want to work with. And we can make the spectroscopy of a single plate very carefully, and we see that indeed in this frequency range it's the DXY modes that we excite. So this is the band we want to play with, and you see there are two peaks because it's a two-band model with a gap in the middle, and we're going to analyze it now a bit more. So that's what we did here. Now what you see here is that we take a spectrum at every site. So at every site, this is now at one frequency. We measure how much energy do we pump into the system if we excite here and measure here. And then we put the mask on these measurements up here. And this mask is very, very pedestrian. We just say we take it only from the bulk. So we leave out the outermost line. And then we take only these lines, or we take only the four corner plates. And that's how we separate these energies, sum it up over these masks. And that's the result you get over here. So you see, we indeed have a two-band model over here. That this is the lower band, and then this is the upper band. And you see that in the bulk, there is indeed a gap, but on the edge, there is also a gap. There is no excitation around 74 kilohertz, but then we have four modes localized at the corner in the middle of the gap. And these are these four corner modes of a higher order topological insulator of this model that they put forward. And
So is phonon they are not degenerate?
no, the degeneracy of these four modes is given by the particle Hall symmetry that the Hamiltonian has, and we are very far away from being very good with our model. I think if I can go back, you see that's the assessment of our model, and you see all these next to nearest neighbor hoppings that we induce. These are just second order effects, and because we have them, we don't implement the model correct. And that's why we don't have particle Hall symmetry, that's why these modes don't run away. That's a very good observation. The first submission of the paper, we had even worse data, but the referees seemed not to have cared. And then we said, by the way, we have even better. Okay, so that the story of this higher order TI was, of course, we were not the only ones to play this game. There is a microwave version, like optical. There is an electrical version of Ronnie and friends. So we were not the only one trying to implement that model, but we were happy that with the mechanical platform we could be really fast, despite the fact that we did it with this kind of the elastic wave, which is the most difficult ones of them all. But it still it shows you what the versatile platform with these mechanical degrees of freedom are. We're not bound by chemical stability, and then you know there is always this disorder that kicks in. Like, well, you also have disorder, but the design degrees of freedom are much simpler, but also the design space is continuous, and that also means it's a bit harder to explore it, because I'm not, you know, I don't need to only sample discrete things that can exist. That might be a thing to say. Okay, then a few more details. You see that indeed it's only, you cannot, whenever you have a topological system, most probably there is a transition you can induce to the trivial one, and that's a similar sample in the trivial phase. So that's just, you know, it works out. And we've seen that already this morning. So these higher order TIs also exist for electrons, of course, this time not the quadrupole nature, but just to say that, you know, these band effects are there for electrons, are there for classical degrees of freedom. The interpretation of what you see is very different. Often in electronic physics, you target the Fermi energy, and then there is some linear response coefficient that is dominated by the very topology you have, a whole conductance that is quantized. We don't have that in classical systems. We don't have a linear response reality to these topological systems. We don't have topological phases, right? We have some band structure that if you excite it, it has these edge states, but it's not a thermodynamically relevant thing. But for applications, you can still use. Now here, the applications that I typically put forward, okay, now take your corner states, put them together, you get nice 1D channels in 3D. That was what I thought could be a route to applications of these things. And I think I was wrong. And I think what really was the key thing that we contributed was to have a good tool to turn this into that. Like that we have one approach to solve the inverse problem of I give you a simple, you know, ball and spring model that has some nice physics, and you make a device out of it. And it doesn't work like in all generality, but it works for this perturbative approach where you can have a frequency gap of the one mode you play with all the other modes. You need to arrange for that, and then inside this if you have some narrow band application that you want to target, then you can use. We're not going to work for thermal applications where you need to have a broad spectrum, but for a clear, well-defined spectral range that you want to work with, this is working well. So that, I think that was the key contribution, and I tell you why. And I tell you why by saying, hey Siri. I hope my phone is not jumping in. No, it's not. Hey Siri, it's zero power consumption. So that's the thing we try to solve. A device that is on a wake-up call while not using any power. So that's the thing we want to move towards. So we want to have a device that reacts to me saying, hey Siri, and then trigger some event in maybe some IoT device or in my phone or wherever. But I don't want there to be, maybe the phone is not a good example because it has a battery anyway that I need to charge because I play with it all the time. But some IoT device on a turbine that is just waiting there to be activated by some external trigger without it having to drain the battery. So that's the goal. And the challenge, I said already that, an IoT device which is waiting for a wake-up signal, the phone, or the last point is taking it a bit further, but I want to show that there is a route further, is if you do computing with mechanical degrees of freedom, sounds very stupid because we have very good computing devices based on electrons. But the moment you move a charge around, we all know that that's not good. And having a mechanical degree that does the job for us could be much more energy efficient. And if you think of having to, I happen to stand in, let's say, Andreas Wallraff's lab every once in a while where he controls his qubits. And, controlling a few qubits is already, a rack that produces tremendous heat. If you want to scale that to a useful device, you need to work on your control electronics or on your control phononics. And that's just the route we try to take. That goes more into a multi-purpose phononic computer. That's not what I want to show you today. I want to have some analog device that just solves one problem. And that's the problem that I try to solve. It's a bit simpler than waiting for Hey Siri and not Hello Google, but just make a binary classifier between 3 and 4. Meaning I want to have a device that can distinguish between the 3 and the 4 without using any power. So that's the goal. That's the challenge. That's what we want to do. It's a bit like detecting a Hey Siri, but just a much simpler version thereof. And with mechanical degrees of freedom, of course, that's not entirely hallucinated because there is a mechanical device that can distinguish between one pure tone and another, and it's called a tuning fork. Right? A tuning fork reacts to a very specific spectral feature. And what we try to do is just a slightly more complex spectral feature than a pure tone is a 3 and a 4. So that tells you that most probably it's going to work, or at least there is a good reason why it could work. And that's the system that we have in mind more precisely. We have speakers that just excite from the side an array of oscillators, and I measure the energy in the middle. And I want the middle plate to be excited like crazy if someone says 3 and sit still if I say 4. And then that's just then a proof of principle application. It can be then that this is maybe connected to a piezoelectric material that if it's excited, it does send some electric signal. It's just that it's at the end of the day, I want to have a binary classifier made out of a mechanical oscillators that reacts to something. That's as simple as it is. But now I need to find the structure. And that's of course not a simple task. And you see there is some resemblance to the higher order TI. So we play with the same degrees of freedom that we know. So exactly, we want to measure one thing. And then the training thereof, I already gave it away. We call it training. These days you don't learn something and you don't fit something, you train something. And it goes very simple, right? You expose the structure to many voice samples 3 and 4. Google has that for you. They have a catalog like they have with the numbers and with the cats and the dogs. There are databases of 1, 2, 3, 4, 5, 6, 7, 8, 10. And you just expose it to many 3 and 4s, and you measure how well does it distinguish between the two. And then if it doesn't distinguish very well, then you you change your geometry such that it distinguishes it a bit better, and then you update the structure, you do it again, and it's like you would train a neural net, if you have any experience with that. If not, it's just, you have a set of weights that you change in order to achieve a performance. And that's very simple and well defined. The problem is assessing what the thing does is extremely costly, because doing a full elastic simulation of such a structure is extremely expensive. And I tell you why. Why we work with this perturbative setup, that's beautiful, because you know what you do. But that means you have extremely small features for these weak couplings with respect to the size of a single plate, and certainly with respect to the size of the whole system, such that you have a huge dynamical range of sizes that you need to cover, meaning it's just your finite element simulations for nuts. That's one thing. The other thing is the topological insulator was trivial, well, it was topological, but it was trivial because it was a periodic system. It had a unit cell of 4 sides, and then you needed to take care of understanding what's happening in these 4 sides, and the rest is, periodic. Here, you need an aperiodic structure because you want to harness the kind of the computational power of distinguishing these different signals by harnessing the full kind of parameter space of these 49 plates, meaning they're not going to be periodic. They're going to be totally random, not random, but you want to have the freedom to change them all individually to achieve the expressive power that your neural net has. So, but that makes computation yet more complicated. And so what comes to rescue? You do it like this. You don't model this. You model a mass spring system again. And then you ask yourself, if I excite this with the 3 and the 4, how do I train the strengths of these springs and the local oscillation frequencies of these balls such that I get a maximal distinguishing feature in the middle? That's easy, because a mass spring model, we can just forward integrate it trivially, but you can write down the exact solution even if it's disordered. It's just a 49 by 49 matrix that you need to invert. That's simple. But then you are challenged with again, it's the same challenge as we had with the higher order TI. So you need to turn this into that. And that's where this perturbative metamaterial thinking comes to rescue. And that's where I say, topological mechanical metamaterials helped us come closer to an application is not by harnessing the topological edge states, but harnessing the technology we developed to one thing and can now reuse it there. And I would have never, if Mark Serra Garcia, most probably he always wanted to build this because he has the foresight. Not a really smart physicist and engineer. He knows what he wants. He also knew how to play me, right? He came to me and said, I can build you a higher order TI, and he knew that I will put all the money and effort on that because I really like that. But it helped us to get this thing done. So using the same kind of technology here, that's what you do. You design degree of freedom is holes. That changes the local frequency because this thing, deforms, and if you make a hole, it's less resistive towards bending, and B, it has different mass, so there is an effect on the local frequency. And then the position of these couplings changes the coupling, the vertical and the horizontal couplings, depending on where it is. And also that's why you use a mode with a node, because if you put a bridge onto a node, it's not coupling. And if you put it very far away, there is a strong couple. So you have, once you work in this perturbative realm, it's really easy to understand what you do. And then you can actually go about and optimize for such a structure. You build it, and then you have, glue it onto this PCB, or you connect many pieces to your signal, and then you measure the middle side. What is its response to a 3 and a 4. So these are 2 samples this is one woman saying 3 and one man saying 4, and that's what you get. And now you see that hopefully for the 4, there's much more energy in that middle plate than for the 3, and that's how you distinguish. And that's how it looks at the end. So you measure the transmitted energy to that central side, and the blue are all the 3s, and the red are all the 4s. And you see that you have binary classifiers, like a neural net that do a binary classifier or any other classifier. It's a binary classifier that has an accuracy of 89.7%. That's not, it's not if you go to MIPS and you present your best machine learning algorithm to do a classifier between cats and dogs, they laugh at you with this performance. But it's a performance that shows it can be done. And all of this is with linear degrees of freedom. That means that whole system is a linear system. That means it's a linear classifier. If you introduce non-linearities, the expressiveness of that system is much higher. You have much more degrees of freedom to play with, and it gets much bigger. And these are the directions you can go. We also checked, you know, can we, this is now only numerical simulations on the simple model, not the experiment. You can ask yourself, how well can I distinguish between 1 and 2 and 1 and 3, and maybe between 3 of them, and then your performance is going down if you look at it only with linear. In particular, the 2 and the 3 was really bad, only 59% performance accuracy on the classifier with the linear system. And now, if you build in a simple model of non-linearities that you can still kind of control, you see how you can bump it up to 71%. So that shows that using non-linearities in these mechanical degrees of freedom is a way to improve the performance of such a classifier.
Okay, that's a question related to that. So, how does that vary with the sound volume? You said it's linear versus non-linear. So, is the degree to which you can separate 4 and 3 depends on how loud they say 3 and 4?
Well, in reality, very much would, of course.
So you said you're a linear regime, but you must have a non-linear regime in these metamaterials.
Yeah, but what exactly?
What would that be on this
Well, the intrinsic non-linearities of the elastic structure is such that most probably would have to drop a nuclear bomb next to it for it to go non-linear. So because we do work in this perturbative regime, it's not very likely that you get strong, like, elastic non-linearities in the game. What we do here is we combine, we make several of these systems and then combine their output in a multiplier. So you can multiply the output signal, and with that essentially introduce non-linearities. So in this way we go from here to here. I mean, here there is, and this is really a proof of principle only in the sense that all of this only works at, now I forgot what was the carrier frequency here, around 70 kilohertz. We don't speak in 70 kilohertz. So we modulate a 70 kilohertz signal with the 3 and the 4. And we prune that input to be on the proper volume level that we want, right? It's just at the moment, all we can do is have a complex waveform that is then leading to a distinguishing feature. And that complex waveform has to be up-modulated to 74 kilohertz. So that
I would think, for example, that the ability to distinguish 3 and 4 from background noise would be distinct.
Yes.
So then it would be, so the ability to distinguish would depend on the degree of background noise, which would be different for 3 and 4. Or is that not true?
What we take, let's be clear what we do. We take a data set of spoken 3 and 4s, and that's all that goes onto our chip. That means there might be background noise in these samples, and we are safe against that.
But in reality, there always be background.
Yeah, absolutely.
I just wondered how you.
I wouldn't be worried about the background noise. No, I don't think, I mean, no, well, of course, it's something you have to take care of eventually, but I think the background noise is not what bothers me most. It's the expressivity of the system when it goes to more complex classification tasks than 3 and 4. Because that sensor on the wind turbine is not going to wait for the wind turbine to say 3, right? So I think that's much more challenging. But what we try to put forward here is that mechanical degrees of freedom can be harnessed to do logic, and you can do that in a controlled way. And I think that's end of story. That we don't do less, we don't do more. That is actually my summary slide. So I showed you how we can have different platforms to do topological mechanics. There is mass spring models, there is acoustics, 2 trivial platforms, then there is a more challenging platform, elastic waves, but it's the most powerful platform in terms of going towards application, because it leads towards integrated chips, it leads towards just standard technology for if you want to make a circulator to have better Wi-Fi signal performance, stuff like that. So that's certainly the right platform in my opinion. And then the story I want you to take home is follow what drives you. For us, this was topology, and something good will come out. Thank you.
Thank you very much for very interesting talk. So we can turn for questions. Niels.
Yeah, first of all, I mean, amazing talk. And also, the fact that the theorist goes away and does these experiments, and something useful comes out is very, very impressive. I was wondering.
That sounds very negative. As if a theoretician could only do useless stuff.
I mean, you put me out of, you get the feeling that you put us out of the job, right? But I was curious, why did your original idea that you make use of these edge states? Why do you think that you said that maybe didn't?
No, it's not that, absolutely not that I abandoned this idea. That this is still, having very high spatial control of where your modes are can be super useful. In the photonics community, you put your gain medium on your chip exactly where you know the mode will be, or you have a phase matching condition on your edge states that will be perfect because of the chiral nature and gives you a nice combo. And all of these things you can also harness in mechanics. I don't say we should abandon it altogether. I just say the first thing that I really think is a step towards technology. Really seems to me this, and has nothing to do with topology, but has everything to do with topology, because we wouldn't have done this, we wouldn't have had that. So
any more questions?
Why did you choose to use silicon and these sort of square shaped sort of unit cells? But why not another material? Why?
There's absolutely no reason. I mean, the first thing we wanted to do is we wanted to have it, tabletop pocket size, investigatable by our means. So that a big silicon wafer was good. In the meantime, we look at silicon nitride membranes that we can fabricate much better and smaller, and so there is we don't have any emotional attachment to the silicon nor the size. The plate is just you start from the simplest thing you have an intuition for, and you scale it down. I think that was our kind of approach. But it's actually, silicon is annoying because it's crystalline, right? So you need to align your design with the crystalline axis of the thing, and you get it wrong, and everything is not as you should. So I'd rather go for something else, actually.
So you could use, as you said, silicon nitride membranes, and then you could make holes lithographic.
Absolutely. No, that's what we do for we have other systems that we look at. We use at the moment silicon nitride there. The tensile stress is a bit annoying at times, but
You also stuck in a plane. Maybe there was some 3D.
Yeah. I mean, with 3D, you could harness so much more structure, but it's so much more difficult to, I exhaust my.
But then the frequency range will be very different. If you go to membranes and nanometers, I suppose.
Yeah. No, the frequency range, but that you just change with size, right? And anyway, you want to.
Terahertz or something.
Well, terahertz is then you hit the actual underlying phonons, right? But no.
Wouldn't that be interesting?
But I ask you, I mean, if you need an application on the terahertz regime, we do it in that.
I was thinking more like going back to superconductivity. So you're basically controlling the phonons. Can you artificially create phonons that would then couple electrons and create artificial superconductors?
Yeah.
Is that possible, or is that just too far?
No, I think if you want to go to, then you hit what you guys are doing, right? Then you hit the atomistic nature of the thing, and you don't get there with holes anymore. But yeah, sure. I mean, there is you can always.
You wanted no energy, so of course you could use single phonon objects if you go to low temperatures and proper size.
Yeah.
Why can't you do that? Is that interesting?
No, it's certainly interesting. I mean,
it would be interesting then if you went to. I remember Michael Lucas should demonstrated. I think it was the first person to demonstrate single phonon objects of low temperatures. Would that be interesting?
Yeah. I mean, one thing is. Because then actually non-linearities start to get more interesting, and you can make parametric amplifiers and things like that.
On you have this morning, non-linear effects are very interesting topology.
Absolutely.
So what is the connection to your work of non-linear effects that we heard about this morning? We heard about non-linear before.
Yeah.
What do you think? Non-linearity is usually really interesting.
Yeah, it is. But if you put non-linearities just blindly on these topological edge states, at least in a mechanical domain, I know it's rather that you destroy everything and couple everything into the bulk, because you have up and down conversion into the bulk, and then you lose the nice protection. So a bit to get the non-linearities are more fascinating for me to get the logic to do computation. There I think it's super.
So how close are you to doing computation?
What?
How close are you to doing logic with this thing?
Well, this is analog logic, so we're there. But if you want the digital logic, in a sense that I have a multi-purpose computation.
Message to computation.
Yeah, no, I think there we're still actually, Mark again, Sarah Garcia, he put forward a catalog of things that what do you actually need to get it done with mechanical degrees of freedom, because you need to fulfill certain things to have it even to be materializable, and we don't tick all the boxes.
You said here this simulation is in this elastic limit, and actually I'm curious, when we think about phonon, this is corresponding to this acoustic phonon. Is there possible we can see this optical region? In that case, this phonon will have an interesting mode like the EG and E2G, A1G mode.
Yeah, I mean, if you want, if you think in terms of the acoustic and optical phonons of just the bulk material, then this here is already like on the range of the optical phonons, because all the longitudinal simple phonons that they are actually maxing out at 60 kilohertz because of the structure we make, right? It's a 1 millimeter structure, and then that's just giving you the frequency range at which the acoustic phonons.
I see. Yeah, something like a recently I'm thinking about, like looks like your basic unit is also a kind of chiral, right? Kind of your square unit.
I think it's not.
It's not like
at best it's irregular. I mean, you mean because of less, like slightly, like very good.
Yeah. Then if we think about this is a phonon system, like in the lattice, if you localize this chiral symmetry, then the phonon will carry this memory. Like the phonon mode will carry an orbital momentum. If couple, actually do a random experiment, use circular porous light. You can make a difference.
I see what you mean. The chiral nature of these arms for the frequency range we're interested. The only thing that bend here makes is that it's softer for this compression. And there is a rigid body mode where this plate is just going up and down, and we don't want this to come too high in energy. right? Because we don't want it to get in the way of the mode that bends. So we need this to be as soft as possible. Having a super thin silicon bridge here, but straight, it just pushes it, right? It's extremely strongly coupled. So we make all these bends that it can like flop, like every corner here has a reason.
Coming back to this edge state, so how important do you think it is that these are phonons for the protection of this edge state? Is that a big problem? Because I always thought that this protection from backscattering is because there's essentially no other states you can scatter into.
Yeah, but that's independent of them being bosons or fermion, I would say. Right? If I have a mode that has only this branch and not this branch, now nothing fills it up to here to the Fermi energy, but I can still excite this mode here. And once it's excited and hits an obstacle, it can still not turn around. As long as there are no non-linearities that allow it to do this, right? That's exactly why non-linearities here are like just some 5-4 theory on that edge is not doing it very well. But the bosonic nature is irrelevant for the protection, but is everything for the fact that it's not the ground state. Right? It has, these are just high energy stuff that no one in thermodynamics, if thermodynamically they are relevant, the crystal is melted long ago.
Any more questions? Another question. You mentioned running to money, and he uses mechanical oscillators or electrical or something.
No, he uses LC networks. Yeah.
LC networks, and he really did see some edge modes, I thought.
Yeah.
But you don't really see edge modes.
No, I do. I just didn't show any of those. And now I'm not on my computer. No. When we did, wait, I first need to go here, and then when we, in this system, for example, where we really built a two-dimensional quantum spin Hall effect analog with pendulums, we see all the beautiful edge modes. I can show you movies, and you fix a few pendulums that they can't move, and then the wave just goes around it, and like that's all there. But that's kind of 2015 type of physics. That No, I didn't say that. Ronnie, you're not there, right?
Okay.
Maybe I just have a general question from more material side. Do you see the possibility to use the nanoparticles or the molecules, to be integrated into your pattern structures?
Yeah, I mean, you can do it at all scales, right? We were looking into assemblies of nanocrystals that you build lattices of, and then depending on the ligands you put on top, then you have different couplings, and then you can start to design these superstructured phonons according to your will. I mean, I think these games can be played at any scale where you have control, and we just play because. It's pointed out simple-minded theoretician, we just play it on a length scale that it's easy to do things, right? But the moment you want to, I say we do it in a platform that is scalable, but any scaling put to work needs experts and is not trivial. But I think the template is there.
My question is coming from at least the expression which I believe will relate to the transformational effect and also the up conversion for the photonics. Would be that also interesting to you?
Yeah, no, absolutely. I mean, sure. We like to play anything that, maybe I should say anything that has to do with geometry. I have feel some intuition, but anyone who is an expert in putting the right ligands on the right nanoparticles to put, then they can play the same tricks, right? It's.
So that's very nice because you said you wanted devices that operate at zero power.
Yeah.
So how can it be zero power if you're transmitting information and you're somehow?
No, but my me saying 3 provides the power.
Okay, so it's not zero power.
No, not zero power, but the device itself doesn't need any.
So it has to take power from something.
Yeah, exactly. It takes the power from the signal it tries to analyze. And that's the key point here. If it doesn't have to be up converted to 74 kilohertz and you know, all of this, but
okay, any more questions now? If not, then we thank you very much for your talk.